All right, welcome to part 6 of robotic arm manipulation with human experiences and HRL. We are going to be starting the agent class in this video. This is a little bit of a longer one, so let's go ahead and jump in and get to it. So we'll be creating a new file, agent.py, and in the agent file we're going to need quite a few imports. We're going to need OS, import torch, import torch.nn.functional as f, from torch.optim, import atom, it's supposed to be uppercase, from model, import star, from torch.utils.tensorboard, import summary writer, we'll need to import datetime, from buffer, import replay buffer, import time, and then finally from Gym Robotics Custom, import RoboGym observation wrapper. All right, we finally have all our imports. So let's go ahead and declare our class. Give ourselves another space. Class agent object and init. Again, we don't need any of this. We need num inputs, action space, gamma, tau, alpha. We'll go ahead and keep target update interval. That's a variable you might want to play with later. Hidden size, learning rate, and goal. All right. Here we can go ahead and say self.gamma. This is going to be a whole bunch of just some declarations. So self.gamma equals gamma, self.tau equals tau, self.alpha equals alpha, self.target update interval equals target update interval. We'll go ahead and declare our device. So self.device equals torch.device CUDA if torch.CUDA is available, else CPU. And then we should probably print it out, just starting initializing agent running on device self.device. So you always want to check if you start this up and you see that it's running on CPU instead of GPU instead of CUDA, you probably want to take a minute and go figure out what's wrong, because it's going to run very, very slowly. All right, so we can go ahead and declare our critic. So self.critic equals critic, num inputs, action space dot shape 0, hidden size, and our name. And the name we're going to pass in is critic underscore goal. And we're doing this, and actually, yes, we did. Okay, cool. We did include goal. So we're doing this because you're going to be training a different model, a different critic and policy for every single goal. You're going to train one for microwave. You're going to train one for drawer. You're going to train one for, open or start burner. So each one is going to need to be named and stored along with, its goal. Just like we've got human memory microwave, you're going to have a, critic microwave, policy microwave. And those checkpoints, that checkpoints directory is going to become quite large as we go. This project is probably the first one I've put together where the data that you're building is really, really important to later steps in the project. So, most of the things that I've published so far, we have, a single training run to do a single task. And if you wiped out the checkpoints directory, you could just rerun the training script and it's going to learn it all from scratch. It's not really the case for this one. For this one, you're generating a bunch of human data, which you're probably going to put some time into. You're going to be generating multiple submodels that will train on their own. And then, frankly, you're probably going to want to save all that. You're going to want to take some backups. And then you're going to generate do a combined training loop at the very end to fine-tune how those models work together. So this is one where the data every step of the way starts to become very, very important, which is not something that you always see in sort of your standard RL tasks. So that's why we're saving that to goal. So we'll do device equals self.device. Self.critic-optim is equal to Atom. Self.critic.parameters. And LR equals learning rate. Self.critic target is equal to critic. And this is, let's see, critic. Num inputs, action space dot shape 0, hidden size, name equals F, critic target goal dot 2, self dot device again. All right, and then we're going to be doing the same for policy. So self.policy equals policy, num inputs, action space dot shape 0, hidden size, action space, name, and this one we're going to do policy, goal, and then 2, self.device. All right. And then finally policy optim, self.policy optim is equal to Atom, self.policy.parameters, and then LR is learning rate. All right, we're done with the initialization method. Now we need to go ahead and do our action selection. So we're going to define select action, and this is going to take self, a state, an evaluate param, which will default to false. We'll say by default we're training unless we say otherwise. We'll take state is equal to torch.float tensor state.to, and we'll send it to our device, self.device, and then we need to unsqueeze it to get the right dimensions on axes 0. All right, so if evaluate is false, and this is where it comes in using the different methods coming from self-policy sample. So if evaluate is false, then action equals self.policy.sample state. Else, so if evaluate's true, in other words, we're going to take the third item returned and pass it as action. And then we'll just return action.detach.cpu.numpy and the 0th element. All right, now we need to go ahead and do our update parameters method. So that's going to be def update parameters, self memory. Here, let's give ourselves a little more space, make that cleaner. Batch size, updates. So the first thing we're going to do is sample from our memory buffer. So state batch, action batch, reward batch, next state batch, mask batch, equals memory.sample buffer. And you know what? So we should be getting a helpful hint here, except it doesn't know what memory is. It doesn't understand that we're talking about our replay buffer class. So what you can do is after memory, you can say colon replay buffer. You're basically telling Python what that thing is in the same way that in another language that would maybe be more static. In something like C++, you would have to declare that it's a int replay buffer or int buffer. In here you don't have to, but now that we've told it what it is, if I type memory, if I can type memory, now I get all of my helpful hints there. So we can say sample buffer. And honestly, I feel like it just makes it easier to read later on. You won't see me, annotate all of my parameters, but I do like to annotate the ones that are custom objects for reasons like this. So, all right. Next up, we're going to do state batch. We need to convert them all to float tensors. Torch.float tensor. State batch. .to self.device. And we're just going to copy, paste some of these. So this will be next state batch and next state batch can get added. This will be action batch and action batch. This one can be reward batch and reward batch. And for these two, so I need to add an unsqueeze to get the dimensions right. So it'll be unsqueeze 1 and mask batch to mask batch. And then this will also be an unsqueeze 1. All right. Now we get into the actual training and update section. So with torch.nograd, we're going to grab, and this is all default SAC implementation. I think I mentioned in the last video the sort of core SAC update steps were pulled from a reference implementation, and I will have that reference implementation linked in the video description for you guys to go and take a look at. So we're going to say next state action, next state log pi, and underscore, because we don't need that last one. We're going to say self.policy.sample, next state batch, qf1, next target, qf2, next target, equals self.critic.target, next state batch, next state action. Now we're going to take the min of those two. This is one of the things that's going to help us keep some stability. So min qf next target equals torch.min, qf1 next target, qf2 next target, minus self.alpha times next state log pi. So when I say that's going to help with stability, what do I mean? Well, this is supposed to predict the value of an action. So if the first network predicts that the value of the action is 1, and the second network thinks that it's 2, well, we want to take the minimum. We want to take, the lowest value that that network thinks the action is, so that if one of them has a very high expected value, it doesn't throw off training. It doesn't, make the agent go in that direction because one network thought it was higher. We take the minimum of the two. So we can say next Q value equals reward batch plus mask batch times self.gamma times min QF next target. And I actually don't need those params there. All right. Now we can go down and say QF1, QF2 equals, and now we're playing with our regular critic, not our target critic. So state batch, action batch, QF1 loss equals f.mse loss, QF1 next Q value, QF2 loss is f.mse loss QF2 next Q value, and then the combined just QF loss is going to be QF1 loss plus QF2 loss. All right, and then we finally get to our update the critic network, and we're going to say self.criticoptim.0grad, zero out the gradients. We'll do QF loss.backward, and we'll do self.criticoptim.step. Okay. Next, we will do start working on our policy network. So pi log pi underscore equals sample. And by the way, if you should pay attention to where I'm putting the underscores. These methods return a certain number of parameters. The underscores are meant to capture parameters that we are not going to use safely. If you don't have them, it will error. So we'll do self.policy.sample with state batch, QF1 pi, QF2 pi equals self.critic, state batch pi. So think about what we're doing here. So we're taking basically getting a batch of actions from the policy, and then we're asking the critic in this state and action whether, what the value of those batches were or of those actions were. So basically, hey, you have a state, you took an action, hey critic, what are the values of those actions? We'll do the same thing we did earlier. We'll take a min QF pi to avoid overestimation of the value. So we're going to do torch.min QF1 underscore pi, QF2 underscore pi, and then we can actually do the policy loss. So policy loss is self.alpha log pi minus the min QF pi, and we're going to take the mean. And then we can do the same thing here. So self policy optim dot zero grad. We'll go ahead and comment, update the policy network. add some comments here, compute policy loss, and compute critic loss, just so we can keep it all straight. All right, self.policyOptim.0grad. I need parentheses after that. So policy loss dot backward. Self.policyOptim.step. Okay. And then we'll go ahead and take our alpha loss is torch.tensor 0 self.device and alpha tlogs equals torch.tensor self.alpha. And this is just to generate some of our logs. If updates percent modulus self.target update interval is 0, soft update. Okay, we're going to put a to-do here. We need to define soft update function. We're going to need that later. All right, and then we will return qf1 loss.item, qf2 loss.item, policy loss.item, alpha loss.item, 0, well, we won't do that one. We'll do alpha tlogs.item. Okay. And it doesn't like something. Oh, does it not? I see what I need to do. Because I added a to do there, I need to add a pass. Otherwise, it's going to complain at me. So, all right, that gets us through agent, select action, update parameters. We are going to go ahead and write our train loop and our test loop. So let's keep going here. Def train self env memory episodes equals we'll default it to 1,000. Batch size we'll default to 64. Updates per step we'll default to 1. Summary writer name, what do we want our summary called? We'll default to blank. And max episode steps we will default to 100. Okay. So setting up TensorBoard. And if you haven't used TensorBoard before, this is going to give us a really cool way to graph and chart the data as the agent trains, so that we're not just waiting for the end to generate some kind of graph. These things can train for many hours, so you really want to see that data, somewhere as it's happening to know if things are going well, or at least I do. So summary, writer, name. I try to make these kind of descriptive, but also something that's going to update every time. So it's going to be runs / datetime .now .strftime %y dash %m dash %d, and this is just your ftime format. And then we're going to do h %m %s, which should do hours, minutes, seconds. So that should make each one of these unique. If you kick off 2 separate runs, they're not going to overwrite each other. And then I'm going to add summary writer name. So what that effectively does, if I pass in that this is, I use these for description sometimes. If you're only doing a couple things, you could say run 1, run 2, just so you know which one you're looking at. But sometimes if I'm trying something different, I'll do a run, by default, and then I'll throw in maybe intrinsic curiosity on one to see if that helps. And I'll throw that in the name. I'll try different parameters for alpha and throw that in the name. So what you end up with is a long string of runs that show the different things you've tried and let you compare how those look on the graph. And that can be really, really useful when you're trying to put these things together and figure out what works. So we'll define writer, summary writer with summary writer name. We'll be using this object later to actually write the data. So we'll say total num steps, we're going to start at 0. Updates, we're going to start at 0. And then we'll say for episode in range episodes, episode reward is 0. Episode steps is equal to 0. We'll start out with the done is false. And state equals env reset. Okay. Oh, env dot reset. That would help. That would help. Okay. While not done and episode steps less than max episode steps. And yep, I see over here I did while note done. Action equals self dot select action state. If so basically this is so we've got one loop, the train loop, that actually does the training. If you recall earlier, we built in functionality into the memory class, so that or the replay buffer class, so that it could tell us if it's able to sample. So this is where we're going to use that. This is another place where we're going to annotate that this is a replay buffer, so that we get our helpful hints here. So now I can say if memory dot can sample batch size equals batch size, then for I in range updates per step. And we're probably going to have this at 1, so this will just be a single loop, but again, it's a variable you can play with. So we're going to say critic 1 loss, critic 2 loss, policy loss, int loss, alpha equals self.update parameters, memory, batch size, and updates. Okay, and then we're just going to do some logging. So we'll say writer dot add scalar loss slash critic 1. And you can log whatever data you want. This is the data that I found useful, but definitely play with this and get the metrics you're interested in. So critic 1 loss, updates, and then we're just going to change this to be critic 2. Loss policy. We'll do entropy. Let's see. We probably don't need entropy loss. We'll do it anyway. Equals ENT loss. Prediction error. No, we don't need that one for sure. Getting rid of that. All right, and then down here, we probably just shouldn't log alpha. We're not going to change it. We shouldn't log it. Shouldn't need to. All right. that should give us what we want. We're going to say updates plus equals 1 to go ahead and increment. All right, now outside of our if, we're going to say next state, reward, done, and then we don't need those two, equals env.step action. We'll go ahead and increment episode steps plus equals 1. Increment total num steps plus equals 1. Do episode reward plus equals reward. And then we can say mask equals 1 if episode steps is max episode steps, else float not done. And we'll go ahead and do memory dot store transition state action reward next state and mask. So that's going to go ahead and start building up our buffer. And then we can finally say state equals next state. And we will, you'll notice I'm now tabbed in one to the left. We're out of our loop. So the episode is finished. We're going to do writer.add scalar reward / train. And this will be where we plot the episode reward, which is really what you want to see. Like, this is the real data point. These are, you know, giving you some information if this goes wrong. So I'll do episode, and then we'll give ourselves, so print episode total num steps, episode steps reward. And I think you have probably seen I prefer to use F strings. This one gets a little unwieldy if you do it that way, so I'm just going to do it this way. Episode total num steps, episode steps, and then round episode reward to 2. This really probably isn't necessary for this one, but it is for some of my other environments. So I'm going to leave it in there. And then finally, if episode modulus 10 is 0, so in other words, every 10th episode, I'll go ahead and call self.save. We don't have a self.save checkpoint yet. So I'm going to go ahead and just define save checkpoint with self and put a pass in, so that we can finish up this section. Self.save. Okay, same issue we saw before. I need to tab it in one, or tab it out, I guess you could say. .save checkpoint. Okay. With that, I'm going to say this video is getting a little bit long, so I'm going to go ahead and end this one here. In the next video, we'll go ahead and fill out the rest of this train method, as well as the one to do that we put in here, and then after that we'll get a test method together, and you know, start to get to where we can train and test our agent. So I will see you in the next video.